In this video, we are going to discuss the geometric mean. So I'm going to write down what that is. We have a similar symbol here, x bar, but we're going to put a subscript of a g to mean the geometric mean. And it is defined by x1 times x2 times all the way up through x sub n, all raised to the 1 over nth power. So we take the nth root of this product. Alternatively, we can write this out as the nth root of, and just like we had a summation symbol, there is a symbol for a product, which is capital Pi instead of the capital sigma. But everything else is the same. We use the same expression here, x1, x2, and so on, and then this ranges from x equals 1 to n. All right. Or, in other words, we can write it like this as well if we don't want to use the root symbol. All right, now how is this related? Remember that the arithmetic mean is that we take all of these values and we add them up, and then to find the average, we divide by the number of values. Here, in the geometric mean, since we multiply all of our values, to kind of go backwards here, now since we are multiplying, we need to take the root, and in particular, we need to take the nth root of that value. And that'll give us something called the geometric mean. Now, what is this useful for? Well, we're going to write out the geometric mean as a rate of return. Or often it's just called the geometric mean rate of return. And the formula is very similar. We use an R here for rate of return. And we have the subscript G to mean a geometric mean. And our formula is this. It is 1 plus R sum R1 times 1 plus sum R2 times 1 plus some r sub n, all raised to the 1 over n. And then because we are adding 1 each time, we're going to subtract 1. That's just a little trick we have to do to make sure we don't deal with any negatives here. Because these rates of return are going to be generally between -1 and +1. And so we add 1 to each of these values in order to avoid any negatives multiplied in here. Okay, and what are each of these things? Well, where R sub I is the rate of return in the time period I. Okay. And so now we're going to do an example to see what all of that means and clarify this information. But we're going to be using this formula to calculate our rate in just a few minutes. But let's write down the example here. So our example says, suppose that we have a $10,000 investment. At the end of year 1, the investment decreases to $8,000. At the end of year 2, the investment increased back to $12,000. So back above our original investment. So after 2 years, we have a 20% increase from the original investment. Okay. So, what do we want to do with this? Let's consider this problem where we see that we have a 20% increase from the original investment after 2 years. And what if we wanted to know the percent increase we have to do each year to go from $10,000 up to the $12,000 that we ended with after 2 years. But we want that percentage increase to be the same every year. So we can't first decrease down to 8,000 then all the way up to 12,000. We want to see what essentially this average percentage increase is. And that's what we want to calculate here. So the first thing we want to do is we want to find the rate for each year. So what was the rate of increase for each year? Well, that is the ending value for that year minus the starting value for that year divided by the starting value for that year. So this is negative 2,000 divided by 10,000, which is negative 0.2 or minus 20%. R sub 2 is, all right, our ending value for that year is 12,000. Our starting value was 8,000, and our starting value was 8,000 for that year. So we get 4,000 divided by 8,000, or in other words, 0.5 or 50%, right? We had a 50% increase if we originally had 8,000 at the beginning of the year, and then we ended that year with 12,000. So those are the R1s and R2s for our formula up here. So let's go ahead and plug all of that into our formula. So we have R sub g here is equal to 1 plus R sub 1 times 1 plus R sub 2, all raised to the 1 over second power. So we're just taking the square root here because we only have 2 values. So it's only over 2 years. And then let's go ahead and plug in all of our information. This is 1 plus a negative 0.2 times 1 plus positive 0.5. Take the square root of that, then subtract 1. This is 0.8 times 1.5, all raised to the 1/2 power minus 1. So 0.8 times 1.5 is 1.2, all raised to the 1/2 power, then subtract 1. Well, this is approximately 1.0954, right? We're rounding here. We're taking 1.2, we're square rooting that, and we get 1.0954, but then I'm rounding to that value. Minus 1, which is equal to 0.0954, or 9.54%. And again, this is an approximation. So what does this tell us? That tells us our average rate of return over those 2 years. In other words, if we invested $10,000 and we were guaranteed a rate of a 9.54% increase on our investment each year, then at the end of 2 years, we would end up with $12,000 if we started with $10,000. So let's check that real quick. Just to do this quick arithmetic, at the end of 1 year, we would have 10,000 times 1.0954. That would tell us how much money we would have at the end of the first year. And then at the end of the second year, if we increased by 9.54% again, then we'd have to take that value and multiply it by 1.0954. And this is approximately, or actually I think equal to here, we're not going to need to round here, $11,999 and approximately 1 cent. Now, we didn't, of course, get exactly 12,000 here because we did round this value when we took the square root. If we rounded this to more decimal places, this number right here would get much, much closer to 12,000. And in fact, if we go far enough, it will be practically 12,000. So, again, this is what our calculation does. It tells us our average, essentially, rate of return, or in other words, our geometric mean rate of return. And that will end this video.